We have 3 talks this afternoon. The first speaker is Shubham Sinha from ICTP. He will be talking about quantum K-invariants Quot schemes.
Okay, so thank you for giving me the opportunity to talk here. Today I'm going to talk about my joint work with Ming Zhang, who is at UCSD. So let's begin. So the basic thing that I want to talk about is, maps from a fixed curve C to Grassmannian, and that's all I'll be focusing on. And we'll see how to find invariants about these. And I mean, it's one of the topics which has been studied a lot. So I'll certainly miss attributing to some people, but I hope I do as much as I can. Okay, so there are 2 ways of compactifying this space of maps. One is the stable map portion, using stable maps or code schemes. So let me just start with saying something about the history. So this area really became popular after in physics by Witten, and then defined quantum cohomology of Grassmannian, and then Vafa-Intriligator. They gave explicit formulas for, in the case of Grassmannian, for counting these maps. In the stable map side, it was first studied using stable map compactification by Siebert and Tian, and they gave a proof of the Vafa-Intriligator formula, and then this quantum cohomology of Grassmannian. There are like several people who found different sorts of formulas for understanding the coefficients. In the code scheme side, Stroma probably was the first person to really see code scheme over P1 as moduli space parameterizing maps from P1 to Grassmannian. Then later Bertram does couple with Wentworth. They studied the intersection numbers using code scheme of curve, and they obtained the Vafa-Intriligator formula in high degree setting, and then in 2005, Marian and Oprea constructed the virtual fundamental class and gave proof using localization for the Vafa-Intriligator formula. Okay, so now coming to what I'm going to talk about today, the K-theory side. Giventhal and Lee defined the quantum K-ring of X in around 2000s. And for Grassmannian, if you really want to understand the invariants, it was studied by Book and Mihalsha. And recently in physics literature, there has been more interest because of relation to some the Chern-Simons theory and Wilson lines, which I have no idea what these things are. But for example, recently, like we found several ring presentations coming from physics, which was proven by Gu, Mihalsha, Sharpe, and Zhou. And in fact, if there's still some conjectural formulas for ring presentations when you're looking at flag varieties instead of Grassmannian. And I mean, there's many more spaces you can study. So now let me just briefly describe what I'm going to do today. So in the code scheme side, probably it started with my work with Dragos in 2023, where we found some Euler characteristics of Quot of some topological bundles over the code scheme. In that case, when this is has 0 rank quotients. So, and the way we found these explicit formulas was one by torus localization. So this is for genus 0, and for genus greater than 0, we prove universality of these power series in you know, like the one Lothar talked about. So and combining the two, you get the formula for these invariants. So with Ming, what we are hoping to do is so note that so this is all for code scheme of zero-dimensional quotients. I'll define very soon. But the universality does not hold when you're looking at a code scheme of higher rank quotients. So you have to consider some invariants. So torus localization works, but this does not work. So today's aim is first of all to look at as follows. So first, what we are going to see is that these invariants of code scheme help us recover the known formulas for Grassmannian. So essentially, like the ring presentation and all the formulas, like most of the formulas you had before, maybe not the best ans, but so this is all in genus 0 setting. But to actually calculate the invariants for higher genus, the second thing that we do is find a TQFT structure that I will describe later on. So essentially, instead of universality, you use TQFT to get formulas for higher genus. And at the end, I promise you to give you new formulas for these invariants. So essentially, I would like to call it like Vafa-Intriligator type formulas in the K-theoretic setting. Okay, so now I'll go into some notations, and it can get a bit heavy on notations, so bear with me. So let PR be the set of partitions with at most R parts, and PRK be the set of partitions inside an R cross K box or rectangle. So for example, let V be 3, 2, which is a partition, and for any given partition you can, and the box you can consider the complement partition, which I denote by V star, which is denoted by bullets here. Now, the K-theory of Grassmannian, or any X, is the Grothendieck group of sheaves or vector bundles with you have to quotient out by the usual relations coming from short exact sequence, and the ring structures comes from the tensor product. So I'm going to give you two bases for the K-theory of Grassmannian, which will be important for us. The first is using the universal subbundle, which is of rank R. So given the universal subbundle or any vector bundle, you can define many corresponding vector bundles coming from that. For example, you can look at the symmetric power or the exterior power. In general, like you can look at the Schur bundles, which are nothing but the Schur functors applied to these vector bundles, rank R. So there's some representation theory that I'm going to assume. If you don't know it, you can just think of these as some vector bundles. So the K-theory of Grassmannian certainly has a basis which is given by the Schur bundle of S, where the partition run over the R cross K box. So here K for me will always be n minus R in case I don't mention. And then you have the usual Schubert basis, which consists of structure sheaves. So you look at x lambda to be the Schubert cycles. Then you look at the structure sheaves of of x lambda, which I call O lambda, which will be, and these will be the K-theory classes in X, and that gives you another natural basis to consider. And somehow using both the bases is useful to study. So if you have two bases, I am going to let A lambda nu to define the change of basis matrix for these two bases, and we'll use it later to define things over Quot scheme. Okay, so now what are quantum K invariants? For me, let me just start with genus 0 stuff. So let EIs be the insertion inside K of X. Then the K-theoretic Gromov invariants are the Euler characteristic over M0 and X comma D of pullback of the K-theory classes from X. And so these are individual invariants, so these are numbers. You can put them into a power series and call this maybe a correlation function with variable q. So note that unlike the Gromov theory, these power series are honest power series, because so in Gromov theory for Grassmannian, you can see that for dimension reasons, it's only finite, it's a polynomial, but not here. Okay, so the quantum K ring is as similar to quantum cohomology is Kx tensor ZQ as a ZQ module, but with a different product. So the product is given by bullet, which is defined as below. So let f alpha beta gamma be a 3-point invariant, and f alpha beta be a 2-point invariant. Then you can consider this as a matrix, so that it's a basis, no? So this pairing matrix, first of all, is invertible as an element as a matrix in ZQ. Moreover, the inverse so we define in F superscript alpha beta to be the inverse pairing, and in these terms, the structure constant is the summation over alpha in the box of the inverse pairing matrix combined with the 3-point invariants. So Keventhal and Lee defined this, in general, and proved certain basic properties, that it's a ring, associative ring. Note that here that these, as I mentioned, that these are honest power series, they're not polynomials. But when you do this, the sum, you actually get a polynomial, which is usually called the finiteness of a quantum product, which is not clear from the definition. So you actually have to prove it. And one interesting that something that interests me when I first saw it was that this has a symmetry, that when you replace nu and mu with the complement partition, so you get the symmetry in the coefficient, which is not at all clear from the definition.
Is it a geometric explanation of the symmetry, or?
That's what I'm going to give you. So using Quot scheme, there is a geometric explanation, and that will.
They did this by calculation directly.
Yes. So they did it by So Quot scheme. So we define quantum. So in the next section, we define quantum K theory using Quot scheme and see that, for example, S3 symmetry has and many properties become more natural. So the Quot scheme is going to parameterize short exact sequences of sheaves where Q has degree D and rank of S is R. So note that this so Q can be a sheaf here. It doesn't have to be locally free, but if it is a vector bundle, if it's a locally free sheaf, and then then that defines, so such a point in the Quot scheme defines a map from Grassmannian from C to Grassmannian, because you just look at for each point you look at the stock. Okay, so to define invariants, it's like going back to the general theme here, like look at the quasi map sort of space. So you think of Grassmannian as a GIT quotient. So it's R cross n matrices, but you have a GLR action and you quotient it by it, and you let if the rank is full, you get precisely element in Grassmannian. If it's not, you consider the quotient stack, which I denote by X. So for insertion earlier, we were having Kx as the but now we are going to look at a K of the stack X, mathfrak X, which is actually same as isomorphic to the representation ring of GLR, because this is a contracted to space. And let me just define concretely. So here you had the universal subbundle. I'm going to just denote tilde for the elements in the K theory of the stack. So I should just for the entire duration, we are going to identify this and the representation. I'll keep going between the two. So for any representation V, you can define the Quot scheme invariant to be the Euler characteristic of the Quot scheme of the pullback over the Quot scheme of the pullback of V. And similarly, we can define the correlation function by summing over the variable Q. So classically, you can think of it as over the Quot scheme you have universal subbundle. So it's essentially restricting the universal subbundle to a point across the Quot scheme, which is precisely this pullback of the standard representation. This is the standard dual of the standard representation. Okay, so coming back to the basis, like using the same change of matrix, you can define what I call the stacky Schubert class. So this definition is not really, so this should technically be called the Grothendieck functor of C, but just to avoid notation, I'm just going to call it O lambda tilde. And I'm going to define the dual class. So the dual class makes sense in the next slide to be O lambda star times O lambda star dot the determinant of S tilde. So that's why I said, having both the things is kind of useful. So the first theorem that I want to state is that this dual class is precisely the dual with respect to the pairing. So if you just take the product in the representation ring and look at the Quot scheme invariant, it's actually 1 or 0. So this is non-trivial actually, because you're showing that for all Quot scheme over P1, so all these classes vanish when degree is greater than 0. So now coming to the structure constant. So for shorthand notation, I'm going to let n0 lambda mu nu to be defined to be this object here, which is just take the product in the representation ring and look at the correlation function. And the structure constant is given by so the main probably the first main theorem of my paper is precisely that the structure constant is n0 lambda mu nu. So why is it useful, as was mentioned earlier? First of all, Quot scheme is smooth, has torus action, it's very well studied. So you can, and it has, you can really, I find explicit formulas using that. Secondly, as you can see the S3 symmetry directly in terms of just writing down the definition. So essentially, if you switch these two and stars, you get the S3 symmetry over Quot scheme, which was not obvious in the stable map side. And thirdly, so note that these were really power series, but for Quot scheme, like the way I prove orthogonality, it's kind of the same way I prove. You can prove that there is a bound on the degree of this structure constant. So I mean, these were all proven before, but it's just telling you that we can do it independently over code scheme.
Sorry, can I just ask?
Yes.
I'm a little confused by the dimensions somehow. In the quote, if I view the quote scheme as the stable maps in this way, there's a parameterized quote.
No, so you mean if there's a point?
That P1 has coordinates, right? So am I not, don't I have to remove the PGL2 action?
No, I mean, you don't have to remove. So the dimension of, so it's just the dimension of this object, right?
Like, but you're saying that's the same thing as like it's the same as the dimension of M00 for Grassmannian?
No, I'm not saying that.
Oh, it's not, okay.
Oh yeah, I'm not saying that. So maybe M03, yeah.
03,
Yeah. Yes. But I mean, I've not explained how to compute on the other side at all. Okay, so I'm not going to discuss proofs in general because I don't have much time. But so let me tell you that. So this slide is about So how we prove it is by looking at. So we first show that the 3-point invariant without the star is actually same. And so is the 2-point invariant. However, when you put a star, so if you can put a star on the stable map side, and you can put star here, and they are not equal. And the reason for that is so when you're doing, so suppose this is your R cross K box, and you have nu, and when you're multiplying with the determinant of S, you actually land somewhat possibly outside the box, and the wall crossing, I mean, things become more complicated. The wall crossing as it is does not go through, and so it's kind of a subtle point here. So yeah.
Is there a concrete description of this correction term?
Actually, so there is. So I mean, if the concrete description is how you prove the S3 symmetry, like for example. So I mean, these things are well studied. It's just they are just not equal. Okay. Okay. So now let's come to the second part. Yeah.
To prove, for instance, S3 symmetry, you
Yes.
use the first scheme.
Yeah.
You do computation of Quot and use word crossing to deduce.
Yeah. So I mean, you use this theorem. If you agree with this theorem, then it just follows. Yeah. So I mean, I just proved that theorem first, and this comes as a corollary. But I mean, there is a lot of steps going into that theorem. Like there's wall crossing. You have to also use some kind of degeneration formula. Like you have to degenerate the curve to actually. So you want to be able to like kind of patch these two up like in some kind of gluing formula to get something like this. Yeah. Any other question? Okay, so now let's come to the second part of my talk, which is probably the most interesting part to me, which is saying that these invariants constitute a TQFT. So a TQFT, so in our case, it should be valued in the ZQ in ZQ. So essentially, it should be it should take any circle to a ZQ module, and then it would take it to, if you have S circle, it will take it to the tensor product. The cylinder goes to identity, and gluing corresponds to composition. So so now when genus is no longer 0, the core scheme admits a two-term perfect obstruction theory. It was proven by Marin Oprea, and using Lee, Tian, and Berenfenteke, you get the virtual fundamental class, and then you also get the virtual structure sheaf. So last time I just had, if you just add in the virtual here, all the definition works. I'd like to note that when degree is very large, then over is just the usual O, because so it's very nice. Okay, so the invariants are precisely, the genus G invariants are precisely the Kyber of code scheme of evaluation of, evaluation pullback of the representation that you pick. Okay, so if you take partitions of lambda 1 up to lambda s and nu 1 up to nu t. So these are tuples of partitions inside the box. You can define ng lambda nu to be this code scheme invariant of genus G. Then the theorem says that the invariants ng lambda nu define a 1 plus 1 TQFT valued in ZQ. So how does it define? So our state space would be this K of Grassmannian tensored with ZQ, and the linear the genus G cobordism, the transformation is given by precisely these invariants. So in particular, I've already shown the orthogonality before, which gives you the part about cylinder in genus 0, but the most interesting thing is this gluing formula that holds in this setting. So I should mention that that a gluing formula in the cohomological setting was obtained by Dragosopra and Alina Marian, but somehow the proof there does not naturally extend to here, and the reason is because in the cohomological setting, when degree is large, it's actually the invariants are actually enumerative. Like that means that it really counts the number of points. Boundary do not contribute, and the stable maps and the code scheme side gives you the same answer, and the gluing formula kind of comes from that kind of physics. From things that were kind of known before. But in this setting, even for genus 0 in the stable map side, I don't know of a direct gluing formula like this. But I mean, you have to use so somehow you have to use degeneration, but also along with, I mean, this orthogonality also plays a role in proving this statement. And wall crossing, obviously. Okay, so now let's, so I promised new formulas, and that's what we are going towards. So first, let me just tell you about my next theorem, which I call quantum reduction. So let kappa be the map from the representation of GLR tensored ZQ to the quantum K theory of X, given by kappa V equals summation V O alpha star quote O alpha. So this is a map. So note that when you're looking at the representation in a box, then kappa V just gives you the corresponding V over the K theory in the K theory of X. So there is no term with Q. There's no higher order terms. There's no correction term. However, when you just change the class to, so this is the negative side, which is actually, I mean, if you think about representation, the weight -1 dot 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 -1 gives you, and you look at the kappa of that, you actually get a power series with infinitely many terms. So and you get that as an element in the quantum K-ring because it's there. The third theorem states that this quantum K reduction map is a surjective homomorphism. So the non-trivial part here is not the surjective but the homomorphism. So essentially, you see that they're highly non-trivial. There are non-trivial things happening here, and if you have this as a homomorphism, you can try to understand the kernel of this homomorphism. So the vanishing result that I have not mentioned in the complete form, in fact, gives you, sorry. Okay. So the vanishing result gives you the presentation that was obtained recently in physics and proven in math by Gu, Miha, Sharp, Shu. So we give an independent proof using this understanding the kernel. Okay, so yes.
So so if you use the quantum cohomology, there's no clear formulation, clean formulation.
No. So the same. So these formulas are already proven, but I mean it depends like what you mean. Like I think people have a lot of different machinery. It's a new way of proving it, and once you assume all the theory before, it's kind of comes out of it very easily in this setting. But otherwise, you have to do more work. Okay, so now let's move on to the formulas. So let V be a representation in GLR representation. Then the advantage of doing this proving this degeneration formula is that you can write this genus G invariant in terms of genus 0 invariant. I mean, this is just a classical thing by multiplying it with the representation, the class in the representation ring of O rho times O rho star. So now since we have to get to formula, let me make a remark about the character of representation. So let V be, so for any representation V, the small v x1 up till xr, let that be the character of V. So for example, if you're looking at the exterior product, that's elementary symmetric polynomial. For a Schur functor, it's the Schur polynomial, and as I avoided till now, O lambda is the Grothendieck polynomial. So these are all kind of well studied in representation theory. So for any V, so my main theorem is about this about these invariants is that I wish this was working, but so the Quot scheme invariant is given by the summation over z1 up to zr, which are roots over this polynomial, and you just have the character of V times some simple terms, and when you sum it over, you have to take t power dth coefficient. You have to take some sort of residue, where t is a variable appearing in the polynomial p. So this formula actually is very similar to the Vafa-Intriligator formula for the invariance over the cohomological invariance over Quot scheme, except in the Vafa-Intriligator formula, the polynomial is z power n minus 1. So the roots are roots of unity, but here there is this non-trivial polynomial that plays a role. But my favorite formulation of this formula is the following. So if you are looking at just, so let's look at, if you have so if you're just looking at Euler characteristic over Quot over P1 of S lambda Sx dual, then this is given by taking t power dth coefficient over of the Schur polynomial or z1 up to zn. So these zi's are actually roots of the same polynomial. So, and this lambda plus, so suppose this is your lambda, then you are essentially adding a d cross r block to get the partition S lambda of plus d power r. So why it's quite interesting is as follows. So above I've written this very classical theorem of Fourier-Weisbord. Essentially, they calculate the cohomology of over Grassmannian. So what we're looking at is the example where d equals 0. So Quot is nothing but Grassmannian. And in this case, the formula above, if we just look at the Euler characteristic, so let's look at the Euler characteristic of Grassmannian. of R comma n of S lambda of S. So this is the Schur function applied to n ones. And in here, what you're trying to do is, if you're letting d equal 0, so you're looking at t power 0th coefficient. So essentially, you can let t be 0 everywhere, and you get these are n roots of z minus 1 power n, which is precisely so these are the roots. So in that sense setting, it is precisely the so this formula is at least generalizes a weaker version of Borel-Bott. I mean, one interesting thing that I've been thinking about working on is just to extend it to the level of cohomology, which I mean doesn't seem probably as difficult, but I mean I don't know, like maybe it requires more work. So if you've lost so far, let me just tell you that if you're just looking at the exterior power of Sx dual, then the formulas are pretty simple. So you can specialize to several cases to obtain formulas. And I will end my talk by telling you that whatever I did so far can be done in the torus equivalent setting. So it justifies the title of the conference. And it also, I also have the formula, maybe in slight generality, that you can look at another class which is slightly orthogonal to the classes that we are dealing with, which is a push forward of the universal subbundle, and take the determinant. So it's and take the power L to it, and the formula remains kind of almost the same, except you have to change the polynomial that you were dealing with. So and that kind of and yeah, so that torus equivalent setting shows up in the polynomial itself, so it takes care of everything else. So I mean this is essentially a complete picture of of these invariants so far. So I ended early, which is great. I was hoping that I don't go forward, but since I have maybe one minute more, I can say that these there are natural direction one can proceed from here. So the first is that there are conjectures about presentation for flag varieties that we are working on, and in general, like so the idea is, the general idea is to look at quasi-maps to GID quotients and use that to study the quantum K ring, and in particular, like I would like to, from maybe if someone can tell me if there is such quantum reduction map, so it gives you a nice way to study the quantum K ring in terms of the representation, the group involved in more generality. And yeah, so for combinatorialists, there's still more like this, you can try to prove more formulas, like how we did in quantum cohomology. So I'll end here.
Questions?
Yes.
So when you introduced the level structure parameter,
Mm-hmm.
you had a particular range you were considering in.
Yes,
But
yes.
For
So
stable maps, there's a reason why you want to consider this range. Why does it come out this way for you?
For me, it comes out because I can't. I wasn't able to calculate for high range. So let me just tell you. So the thing is that these zi's, when you do the localization calculation, it gives you that these must satisfy this polynomial. But when L is not in this range, the polynomial has more degree than it should. I mean, than n. And then there are essentially extra roots from the polynomial that I don't know how to work with. So in my previous work with Dragos for code scheme of zero rank quotient, like we actually had one extra root, and we somehow were able to manage with that to get explicit formulas, but in general I don't know.
Any other questions?
Yes.
Is there a presentation of the quantum homology of Grassmannians? as the one that you presented?
Yes, yeah. So so again, like I did the whole thing. So after writing the whole paper about quantum K-ring, I'm kind of writing notes about the quantum cohomology. So there is still a quantum reduction, that homomorphism, and you can find, so first to answer your question, Siebert and Tian already gives the presentation. So it's a very simple presentation. It's given by the relation churn of S times churn of Q equals 1. So this is for Grassmannian, but you have to just write, so let me put T to QT power N. I have to check that. So that's the presentation. So and a lot of work has been done about these presentations. About the quantum cohomology.
You probably have said this. So in the reduction morphism, if you replace things, here. So if you replace the quantum K by quantum cohomology, the right hand side, you see this equation, and replace the R of GLR by the equivariant cohomology of a point, a quantum cohomology of a point.
Yes, yeah. So essentially, that's ring of symmetric polynomials, and so that's also homomorphism. Yes, that's sort of slightly easier to prove. Yeah.
The way they find that presentation is the same way.
No. So I think this is more like I've been recently interested in. I don't know if so they find it by explicitly calculating counting the curves and using degree conditions. But yeah. So I like this way of finding presentation. So this seems like a more general way to do it.
So,
yes.
If you is there a way to study like the other like isotropic Grassmannians and things
so
like
that? So that's what we have been thinking about. Like I haven't started working on it, but I don't know like if the same, at least so for localization, yes, I believe that should be true. The wall crossing should also kind of work because of the work of Chocon-Fontaine, and then in the K-theoretic setting by Zhang and Shaw. But whether story is as nice as here, one has to study it and then find out.
But like, if I take X to be some homogeneous space, do you expect there to be like, stable maps make sense? Do you expect there to be? Is there some Quot scheme analog?
Oh, so I don't know for any G mod P. When G mod P is also a GIT, then there is a quasi map. Then so quasi map with fixed curve essentially. So that's the space you should be working. So you can look at flagged varieties, isotropic Grassmannians, maybe toric varieties, and whatever things have been worked out, one should aim to go ahead and do the same.
Okay, if there's no further questions, let's thank the speaker again.